Okay, so we have started the recording. Welcome again to the November webinar, Cloud Native Telco Assessment. For the colleagues who join for the first time, my name is Karim Rabia. I'm an ICT architect. Most of my experience is in the telco domain. I'm currently a senior architect at Red Hat, and I had like previous roles with system integrators, with suppliers, with operators, and also I have some good contribution in the community groups and the standardization entities. So I usually see the technology from a vendor agnostic approach. I'm always trying to map that into content and slides. So today we're going to talk about the cloud native concept. What is the term exactly, cloud native? And we are going to even analyze the different messages in the market to understand exactly what do they mean. And we are going to focus on some of the I would say key concepts of cloud native, mainly the microservices and the source to image. This will be like the second part of the webinar. So we can start, and before we start, any questions, please feel free to post it on the Q&A section. After each set of slides or section, I will have a look and we will conduct a discussion about the questions. So the cloud native is what I call it's a community term. So it has multiple definitions in multiple contexts. Okay, unlike the standard definition that Telco professionals are used to deal with, like the ones in the 3GPP, the ones in the HC. Cloud native may have different definitions and different contexts, and even the influencers in the market, like suppliers and technology providers, sometimes they use it in different tracks. So I just gathered some definitions from some context, from some technology providers and groups, and we'll try to extract some terms that actually will give us a clarity about what does the cloud native, I would say, refer to. So let's just review the definitions available in the market and the community, and I'm starting from the Wikipedia. Okay. So I'll just read the definition quickly, and then I'll stress on some words that can give us like a clue about what cloud native might, I would say, refer to. So from Wikipedia, cloud native computing is an approach in software development that utilizes cloud computing to build and run scalable applications in modern dynamic environments, such as public, private, and hybrid clouds. So we gotta stop here, and for a second, let's focus on these terms. Okay. So the cloud native computing itself, it's an approach in software development. Okay. So it's a software centric technology, right? So when someone says cloud native, then we are talking about software applications, about software development. So that's I would say, a main contributor to the concept of cloud native, that you need to have a software centric environment, and you need to have some sort of software being developed. Okay. And that software developed application or software development, it's actually using the cloud computing model to build whatever dynamic application. So it relies on the cloud computing. So in order to understand the cloud native, what's cloud native, you need first to understand what is cloud computing, what is the cloud model characteristics, and that actually will be on the second slide. There are technologies like such as containers, microservices, serverless functions, and immutable infrastructure deployed via declarative codes are common elements of the architectural style. So it seems that these technologies like containers and microservices and serverless computing are very coupled with the cloud native concept. So as if like cloud native is actually realized or built in these technologies. And that's why it's very common when someone talks about cloud native, he just talks about containers and microservices. So they are coupled in a way or another. If you take a definition from AWS, So again, cloud native is a software approach of building and deploying and managing modern applications in cloud computing environments. So again, cloud native is all about the software development, the new software approach of building these kind of modern applications. The difference here that these applications are not mapped or are not coming from a legacy, I would say, domain. They were not like a PNF physical network function, and then we went for virtualization, virtual network functions, and we just mapped the aspects from the physical legacy domain into the cloud. No, it is natively developed and deployed in cloud using the cloud, I would say, cloud computing environment and cloud computing technologies. So that's a difference. I mean, to be cloud native, this means that you are developing and deploying the software purely in cloud. Okay. And then modern companies want to build a highly scalable, flexible, and resilient application that they can update quickly to meet customer demands. And that's something that I made it bold because cloud native, like DevOps, like all these things, these are all means or tools, okay, to achieve a better serviceability, to be able to adapt to the customer demands, the market demands. So it's just a tool, okay, to make you deliver in a better and an efficient way. For Microsoft, cloud native architecture and technologies are an approach for designing, constructing, and operating workloads that are built in the cloud. So they are natively built in the cloud. Okay, it's not just it's not like what happened in the NFV, for example, that you used to have a physical network function, for example, an MFC or media gateway, and then you started to do a virtual media gateway, and you did just mapping to what's happening in the physical into the virtual. And then we had this kind of mess about virtual network functions not even cloud not being cloud friendly, and take full advantage of the cloud computing model. And that's a very important thing again if you want to understand the cloud native. Okay, what's cloud native? You need to understand first the cloud computing model. And I always say, can you tell, for example, if someone is native Japanese if you don't speak Japanese? So you need first to understand Japanese to judge that this one or this guy is native Japanese, and it is here the same rule. From Red Hat, cloud native application development, you will always see the application development. You'll always see software development. That's a main brick of being a cloud native. Approach of building and running improving application based on well-known technologies for cloud computing, as we said. Organizations adopt cloud computing to increase the scalability, availability of apps, hopefully. And then these benefits are achieved through self-service and on-demand provisioning of resources. If you take these two things, self-service and on-demand provisioning of resources, these are actually the main characteristics of a cloud computing model. So as if it's telling you that you can only achieve these benefits if you adopt or if you embrace the cloud characteristics or the cloud operational models. And then I end the definitions with from the CNCF. And CNCF is one of the well-known Linux Foundation entities. I think they were launched in 2015 with the goal of standardization, the concepts around cloud native, container, these kind of things. The main contribution mainly was coming from Google by upstreaming the Kubernetes coming from Google to that entity. So many professionals and many entities in the community sees CNCF as a standardization body and entity for the cloud native technologies and containers in particular. So CNCF, cloud native technologies, empower organizations to build and run scalable applications in modern dynamic environments such as public, private, and hybrid cloud. And if you see any definition to cloud native, you'll always see that it must be or it shall be capable to be deployed in any environment, private, public, hybrid. And that's what makes the application cloud native, that it's not dependent, it's not coupled with a specific cloud stack. It can be run across any over any environment. Container service mesh, microservices, immutable infrastructure, declarative APIs. These are all technologies enabling, I would say, or forming an application that's cloud native. These techniques loosely coupled systems are resilient, manageable, observable, and combined with automation. So automation also is one of the modern aspects of the cloud native. So this just slide was just to give you a clue about that there exist multiple definitions, but all of them, they are, I would say, they have common understanding that cloud native is all about the new model of application development natively on cloud. Technologies are microservices, containers. Cloud native application can be deployed anywhere in any environment. And it has like an aspect, or it relies on automation, self-service, and on-demand provisioning of resources. So as I said, to understand what's cloud native, we need first to review what is a cloud computing model and what are the characteristics of the cloud. So we will focus here on the characteristics, and then we will have a nice slide discussion, okay, like evaluating a certain application, is it cloud native or not, based on these characteristics. So these characteristics are relatively old, actually, and I would say these are the classical 2011 standard characteristics of the cloud. Cloud should provide on-demand self-service. On-demand, like any users can get services from the cloud, like resources, without any human intervention. That's the on-demand self-service. Broad network access, that you can have access to the cloud capabilities through like clients, like applications, like dashboard, like whatever, and you can access any resources on the cloud. It's abstracted and exposed by these kind of clients. Resource pooling, that cloud workloads, they share the cloud resources in a cloud fashion, or in a some sort of pooling. Okay, it's not logic that you get a cloud and then you segregate cloud into workloads. Each workload has its own dedicated resource without any sharing. This is not cloud. Rapid elasticity, that cloud can scale to the application requirement. If there's a need to do scale out, cloud can have the capabilities to do that. If there is no need for the resources, then resources are taken out, so that's scale in. So this is one of the main aspects or characteristics of the cloud. And then measured service in terms of metering for sake of billing, and in terms of metering and performance monitoring and alarms and logging. So that's somehow hits the concept of service assurance on the telco side. So these are the characteristics. So let's now do some practical evaluation, and it will be a discussion. I will also need, I would say, your comments here, but let's take it one by one. So these are the characteristics. This is actually the classic characteristics of the cloud 2011. And let's now interpret the messages that we used to hear in the market from suppliers, from operators, from influencers, from system integrators, and let's judge together. So we have a case, for example, that application supplier insists that the application must run on a specific cloud infrastructure. And that was a common case. So when you like starting from 2013 even till today, that like vendor X, he's actually providing a certain core function, let's say mobile core function, and then for some reasons he say that, okay, this core function, for this function to behave correctly, to meet the performance, to work in an efficient way, it must be onboarded on a certain cloud stack, and most probably it's his cloud stack. So this case 100% makes the application, for sure, it's not a cloud native, because it's very coupled to a certain software, a certain hardware, and this is not a cloud. A case where a certain cloud provider plans to migrate all applications from the cloud to perform software upgrade. Imagine that you have a cloud running workloads, and then you need to upgrade the cloud itself, Cloud OS, and then for some reasons you need to migrate all the applications to not interrupt their serviceability or to not impact their performance or whatever. this is not a common approach. And this doesn't make even the cloud itself. It's a cloud native from a cloud architecture perspective, and also applications are not cloud native because they are somehow dependent on the cloud itself. And this is not what cloud native all about. When you're going to see the containers and microservices, they are very isolated from the operating system itself on the cloud. So the promise or what we target to achieve from Intellicus, and that actually will counter the pain that we saw with the beginnings of the OpenStack, is that we need to do the upgrade, like in-service upgrade. You don't need to migrate the workloads and then do the upgrade and get back the workloads again. This is a very classic legacy way of doing upgrades. You may get this message from the application supplier when he says like, okay, application does not support auto scaling. So how does this make it a cloud native? Because cloud native, you need to have this rapid elasticity, right? You need to adapt whenever there is an increase in the demand. You need to scale out. Whenever there is no demand, you need to scale in. So this is not a cloud native application. Every time you scale out the network function, you need to update the IP addressing manually. And we saw this case many times in the NFV, that NFV, the VNF is based on something called VNF components, and VNF components was based on virtual machines. So every time you scale out, you add a new virtual machine. So every time you add a new virtual machine, you have now the headache and the pain of what is the IP address that this VM gonna have, and if it get it in an automated way, how it will be discovered by the other systems. So we unfortunately, many of the vendors didn't support auto scaling because of this point, because they said, okay, we can scale out, but the IP address, what they call the service configuration or day one, day two configuration, who will do that? Who will automate that? So this is not a cloud native approach. We had the case, I would say during the last year, that okay, VNF is based on virtual machines, but the VM itself, the virtual machine itself, it has a flavor that require, for example, a huge number of virtual CPU. So here, for example, I'm bringing a 38 virtual CPU. 38 virtual CPU, if we go with hyper-threading, that's more or less 19 physical CPU. This means that this VM most probably will capitalize on a certain socket, server socket. So this is a very heavy weighted VMs. And this is very opposite to the concept of cloud native bringing the lightweight applications, the lightweight CNFs. So this is not a cloud native as well. By the way, all these messages are real and practical messages that we see in the market. VNF components must run on specific hosts or specific configurations. Some vendors mandate that their internal components of the VNFs must run on a specific hardware configuration, on a specific NIC card, on a specific storage configuration, on a specific, I would say, accelerator. So this kind of coupling the software part, which is the VNF component, with the hardware, it's a very, I would say, it makes it not a cloud friendly at all, not even being cloud native, not cloud friendly. And this is very common, unfortunately, at least in the last, I would say, 5 years, between 2014 to 2019, before the rise of the containers. Application support scale out, but scale in is not supported. And this is very common on some of the telco applications. They do supporting scale out to cater the high demand, but they don't support scale in. But what's the point? I mean, if I'm a cloud provider, you had the resources to cater the demand, but when the demand is off, is not needed anymore, the resources, you don't take it off. So I'm giving you more than you want or more than you deserve. So this makes the application or the VNF not cloud native. If you have any other messages that you have heard in the market from any supplier or customer or system integrator, please write it in the chat and maybe we can discuss it. But these are, I would say, the main things that makes the previous generation of telco network functions not cloud native at all, not even cloud friendly. Last one, and this is like a brand new one. And starting from 2019, we started to see the rise of the containers and the CNFs, even that was very aligned with the rise of the 5G deployments being containerized. But some application suppliers or some network functions suppliers, vendors, they say, okay, we run on containers, but we would like to have our own Kubernetes cluster. We don't want to share the cluster with any other network function. And for the colleagues who are maybe not familiar with Kubernetes, think of OpenStack or VMware, that you have some sort of an OpenStack deployment or zone or whatever, and a certain application, they want to get their own dedicated cluster, OpenStack cluster. So this gives an impression that they are still coupled with the cluster itself, with the software itself of the cluster. So, for example, they are very worried that they may need some tweaks on the cluster itself, and that would impact another network function. So this what makes actually the operator or the customer suspicious about telco network functions being cloud native or not, because we get such requirements in the telco domain only that we run on containers, but we don't want to share the cluster with any other application. So we would like to get a dedicated Kubernetes cluster. This makes it non-cloud native. Any questions till now? If you have any questions, please feel free to put it on the Q&A or the chat. Okay, so those were the characteristics of the cloud. I mean, coming from 2011, okay, the classic characteristics. But with the evolution of the cloud native technologies and practices, and even the rise of the containers, there are now some new modern characteristics that you can use to benchmark or to evaluate if this application or if this architecture is cloud native or not. So if you see the terms like microservice, containers, S2I, which is source to image, automation, orchestration, location independence, DevOps, DevSecOps. So for example, for microservice, the new approach of developing the application itself, not a monolithic application, but a set of collaborating and very independent deployable modules, which is a microservice, and the very lightweighted. This is actually a very clear practice of being cloud native. And to make you understand what is a microservice, think of any telco function or any network function that has control plane, user plane, O&M module, lawful interception module, something for encryption. So all these parts can be seen as independent microservice. So you have a microservice for control plane, microservice for user plane, microservice for front end, microservice for back end. So this is how you architect or construct your network function internally or the application internally. So that's a very common practice of being cloud native, and to have this microservice based on containers, and because that's actually a perfect fit due to the nature of the containers being lightweight, and it maps perfectly to the concept of microservice with the concept of containers and pods. Third thing, and maybe I talked about that in one of my previous webinars, you need to have some sort of a zero-touch deployment, or what we call sometimes ZTP, zero-touch provisioning. That you have the tools, you have the technology that enable the deployment of the cloud itself in an automated way, the life cycle management of the application, like you deploy the application, you scale the application, you heal the application, you terminate, all these are happening in a zero touch without a human intervention. And this is actually happening by the aid of the automation tools and orchestrators that they're in the cloud stacks. Capabilities to produce container image from source code, and this is something that we will see in this webinar, and that's the S2I, source to image, that you have the mechanism, you have the process and the pipeline that enable developers to code, and then with that technology, this code ultimately is transferred into a container image and then into a microservice. This is actually one of the practices of being a cloud native. And then DevOps, DevSecOps practices are applicable and executable. So I usually get many a question about DevOps and DevSecOps, and I even work on that as part of my job. But if you don't have a cloud native environment or a cloud native application, if you don't have like a software delivery pipeline, if you don't have the culture of DevOps, then how you are going to apply a DevOps? And that's why one of the things that you may judge that you have a cloud native technologies in your organization or not, if the DevOps and DevSecOps practices are applicable. If they are not applicable, most probably you are not using the right technologies, you are not using cloud native technologies or tools or solutions, and for sure maybe the culture and the organization is not helping. So these are like the new things. You can add these new things on the previous slide about the characteristics, and then you get a holistic list of cloud characteristics, even application, even architecture. Follow this list, then we can say yes, this is a cloud native application. So I will take two of these characteristics and shed some light on them and focus on them, which are the microservices and the S2I source to image. So what are the microservices? And as I said, it's a very common practice of being cloud native is to architect or to construct internally the development of your application based on microservices. So as you see, there are different microservices in different colors. Each are actually fulfilling a certain business logic. People working, for example, in OSS, BSS can say, for example, this is an example. This red one is doing service order management. The purple one is doing customer handling. Like the yellow one is doing some CRM functionality. Green one is service decomposition. Uh, Blue one service reporting. So you can easily break the functions of any holistic solution into a set of microservices. Okay, and this set of microservices, they are usually stateless. They don't keep the data, the subscribers' data. And because they don't keep the subscribers' data, you don't care a lot about a certain microservice because you have a mechanism whenever a microservice or a container or a pod is terminated, you will have a mechanism from the platform to rebuild this pod or this microservice. But the state itself is stored in the database. So you don't really protect the microservice the same way you used to do with the virtual machines, right? Because each time a microservice fails, it will rebuild again, and then it will get the state or the data from the database. The API gateway, because most of the modern microservices, and this is a fact, they communicate through APIs, and that was the evolution in the 5G core, for example. I mean, when we went to the service-based architecture, that was the evolution that most of the control functions now communicate with APIs, like the UDM, NSSF, these kind of things. So it's very common to have a certain API service in your architecture fulfilling the API communication between the microservice and even allowing external users to access a certain microservice through this API gateway. So this is on a high level the architecture of the microservices. That microservices are very independently deployed. They communicate through internal logic like service mesh, for example, through the concept of something called service in Kubernetes. They communicate with the external world with the API gateway because they are all talking with APIs. Most probably, and the majority of the modern microservices, they don't store data. They are not stateful. And most of the state is stored in the database. So the microservice itself, if it's faulty or it is down, it can easily rebuild again and get the state from the database. So as a one major characteristics of or a major aspect of a microservice, the thing that I'm drawing here. If you see that the red microservice has its own development team and has its own pipeline. So you can have a pipeline per microservice. So there is like a developer. sitting and working to enhance the features of the front end side or to enhance the feature of the service order management microservice. While there's another purple team working on adding new feature or enhancing the feature of, for example, the service decomposer or doing the new features or the new upgrades for the CRM. And that's the beauty of the microservices, that you don't upgrade the whole system or the whole application as a monolithic system, but each microservice can be handled from lifecycle management perspective in a completely isolated way. So each has its own development team. Each can run their upgrades, their patches, their everything in parallel. They are not coupled and they are not related to each other. Actually, the guy working on the development, he's working in a, let's say, in a serverless mode. Serverless mode, like he's only focusing on his code. He doesn't care about the infrastructure because he is sure that, and he doesn't see that there is a strong technological pipeline because of the process and the tools that will eventually take this code and deploy them in production to be like a container or to be like a part of microservice. So this developer doesn't actually have to understand how Kubernetes works, for example, if you are working on Kubernetes. He just focus on his code. So this is one of the aspects of the microservice, one of the very nice aspects of the microservice. And for us, for example, I worked a lot in the supplier and system integrator seat. So when a customer asks me for a new feature, it's easy for me to identify, okay, that feature, it touches or it maps to that microservice. So I only focus on the upgrade or adding a new feature to that microservice only, not caring about all the other microservices. One common aspect of a microservice is actually that a certain microservice can be shared between two applications. Although this may look a little bit weird for telcos, but yes, it's happening, and it's happening a lot in the IT. That if you have a certain microservice that actually can give some common functions to multiple applications, then why not? Why do we need to redeploy another microservice or duplicate the microservice? So as you see, that this yellow microservice is common to the application X and the application Y. And again, that's a very common thing in the IT. Not that common in the telcos because of many technical and non-technical stuff, but at the end, logically and technically, nothing is prohibiting us to do that. One nice thing about the microservice, and that was a pain point with the virtual machine and with the OpenStack, that in microservice at the end it maps to a number of pods. And pods is actually the smallest deployable unit in the Kubernetes or in the containers domain. So one pod can map to one container or one pod can map to many containers. But at the end, pod is the smallest deployable unit. If you want to put an interface, something like the VNIC, okay, it's actually assigned to a pod. If you want to give an IP address, it's not assigned to container, it's assigned to a pod. So in Kubernetes, solution and container platforms, these pods gets actually an automated IP addresses like IP address 123. We don't care a lot about the IP address of the pod, unlike the case of the virtual machine, because all these pods that actually contributing to the service orange are abstracted by an object called service. Okay, so whoever wants to communicate with the service, he doesn't communicate with IP address 1 or 2 or pod 1 or pod 2. It communicates with the service object. And service object, it has the native capabilities of doing service discovery to understand what are the services that actually it is abstracting, and load balancing. So it gets the request and it has internal mechanism to load balance on the pods contributing to the service. So this is a very nice concept. Why? Because each time you scale out, you add a new pod, you don't care. You don't care actually about the IP address of the new pod. And all the other services, they don't care to actually understand what is the IP address of the pod for, because all these are abstracted by the object service. So I just wanted to bring that to you because there are many benefits of doing microservice. And I know many of you, maybe, or some of you are still working on the traditional NFV deployments, but this is the way forward. And this is actually what is coming with the new wave of 5G and O-RAN. All these are containerized, and hopefully all these will follow the microservice methodology. Any questions before I go to the source to image? So we talk now about the microservice, and microservice, as I said, it's one of the basic bricks of cloud native practices. And as to why with one of them, so that's why I'm bringing that slide to explain to you what is the concept of source to image. Because I believe this one might be like a little bit awkward for the telecos specific, because it's more like a development mentality. Okay, so what is source to image? From the name itself, okay, it's actually a source, which is the source code. So it is a development code, and it is something that will help the enterprise to convert the development work, the source code, at the end into an image. And why an image? Okay, because there's like a direct relation between a container image and a container, which and a container is actually the microservice, or it is actually the thing that's going to be deployed eventually on the Kubernetes or on the platform. So the image, as I'm writing here at the note, that it's actually a binary that includes all the requirements that needed for running a container. It includes called all the operating system variables and dependencies that is needed to run the container. So it's a packaging like a container, okay, packaged in an image. Whenever you run the image, okay, then you get the container. So basically, container is an image in runtime. And if anyone working on the Kubernetes thing, you just pull the image, you do a command like podman command to run the image, and then you get the containers. So it is important that we understand that how the process starts and how it ends. And I will also explain the business logic, because the use cases also is important. So it starts like that, okay? That you have a developer, and having a developer, it's something to be explained. Why would a telco operator have a developer? There are multiple use cases, okay? There are some enterprises that actually have their own in-house developed applications. Some enterprises, some telcos, they develop their own applications, okay? Either it is an internal application or even application exposed to the customers. So that's a use case, that you hire developers to develop applications for your enterprise or for the customers. Or, for example, you are having some sort of edge solution, and you are opening a contest for developers. You are providing a pass, platform as a service, and you are inviting all developers to come guys, develop for us 5G use case, edge use case, and who wins will get a prize, and we will embrace this use case, and we will actually offer it to the market. So there are multiple cases where telcos may have developers. So you have a developer. That developer only understand Python, understand Java, HTML, whatever language, coding language he's using. But at the end, he will produce a code. Okay, and then that code is committed to a repo. Let's say Git, GitLab, or any kind of repo. So it commits the code to the repository. Pushing the code to repository can trigger systems like Jenkins, like this kind of CI/CD pipeline that can actually get the code and start the process of build that code to an image, and eventually deploy the image or to as a container into the Kubernetes production. So it starts with the developer pushing code. For sure, code has multiple releases and multiple stages, but it push the uh, the code or the deltas to the Git, and that can trigger a CI/CD pipeline system to take the code and start doing the image build. Image build, at the end, it gets the code, it gets something called base image, and then with some logic, with some tools within for example, the Jenkins, it produces a Docker image, and that the Docker image is pushed into some sort of artifact or image repository. And then the production cluster, the Kubernetes cluster, is triggered by the same CI/CD pipeline or the same Jenkins to get the image, to pull the image from the image artifactory. And once you get the image and you run the image, you get the container. So what was coded now is transferred into a container in Kubernetes. This is very informative because there are other sub-processes are being done. For example, if you want to push configuration or some variables or how this containers or this pods will behave, so we usually work with Helm charts. It's very common in telcos. So Helm chart, think of Helm chart like if you remember the VNF package and the VNF descriptor of the HANFV, the NFV, it's very similar to it. Even it has the same format. It's a YAML file after all. So for example, this developer can do the code and also can do some template like and put it like in Helm chart and put it in the repo. And that Helm chart also can be pulled by the Kubernetes. So it pulls the image and pulls the configuration. And then voila, you have the service up and running. So source to image, it's very important and it is coming. And I would say most of the telcos are doing the transformation from legacy systems, legacy operational model to new operational model and new ways of software production are actually moving in that direction to achieve this kind of pipeline. Any questions? Okay. So just a summary or a wrap up on what we're saying. So as you saw, cloud native is a very like the buzzword. You need to understand uh, what is the context that it is used in. If it's, for example, describing an application, so it is a cloud native application, and most of the talks are actually talks about that part, like an application being cloud native. So if it's a cloud native application, then it is a software application designed to be deployed natively on cloud. As you see, we made code to be deployed on cloud. So just natively coded to be on cloud. And it are making use of the cloud computing architecture and technologies. So at the end, it was realized by containers or microservices. That's a cloud native application, for sure, with many other aspects that we scanned during our presentation. Some use the cloud native to describe technologies. Like when you say cloud native technologies, most probably you are referring to microservices, to autoscaling, to automation, to orchestration, service mesh, these kind of technologies, supplementary technologies actually helping the cloud native functions for example, in the lifecycle management and these kind of things. Some people, they use cloud native to describe the architecture. Okay, like when you say cloud native architecture. So cloud native architecture can actually be the application, like how the application is being composed. As I said, as I showed you, like microservices independently decoupled from each other, stateless, an architecture that have an API gateway. So this kind of things that makes the application has a cloud native architecture. Some professionals use it to describe the architecture of the cloud itself. When they say that the cloud is cloud native architecture, this means that it provides the capabilities like PaaS services, platform as a service, that realize or that ease the lifecycle management of the cloud native applications. So some professionals use the cloud native to as a term for cloud native architecture of the cloud itself. Last thing, and it's common that people use the term cloud native to describe platforms. Okay, so when they say cloud native platforms, they usually refer to the technologies or the underhood technologies or systems that curates the lifecycle management of cloud native application. For example, the Kubernetes itself, it's a cloud native platform because it manages the lifecycle management of the cloud native application. It provides CaaS, let's say container as a service, and also pass at some level. Okay, the DevOps tools itself, uh, when you deal with Jenkins, with Maven, with this kind of things, Jira, Git, the tools that contribute to the CI/CD pipeline. Some professionals also use the cloud native platforms to refer to these tools. So this is just a summary of on how the cloud native term is used. The slide that I showed, uh, I think it provided an overview about the context of the cloud native in terms of we focus on two things in terms of microservices and S2I, and I showed you what are the factors or the practices of the cloud native. The key thing, the key thing, you cannot judge if an application or if a practice is a cloud native if you don't understand what is a cloud computing model is. So that was the theme or the storyboard of the slides. We understood the cloud operating model, the cloud computing operating model, and then we moved to assess the cloud native practices and the cloud native technologies. I hope that was, I would say, informative to all of you. We finished on time. If you have any questions, please feel free to ask. We still have 5 minutes. Okay. I would like to thank you, and the video will be available on YouTube, and I will keep you posted on in LinkedIn whenever it is uploaded. Thank you.